students. Today I am going to explain important concept, that is Raman effect and quantum theory of Raman effect. The title of the concept is Raman effect and quantum theory of Raman. He is the only Indian greatest mind of India. He won Nobel Prize for his effect. Sir Raman won Nobel Prize for Raman effect. What is Raman effect? And what is the quantum theory of Raman effect? So simply, when a UV or visible radiation, in electromagnetic spectrum we have 7 different portions from bottom to top: radio, micro, infrared, further divided into far infrared, near, very near, visible portion, and UV, ultraviolet, X-ray, gamma. 7 portions of the electromagnetic spectrum. Generally, in radio wave region of electromagnetic spectrum, we can observe nuclear magnetic resonance spectroscopy. Here, where we are able to see nucleon orientation at radio wave region. The second, microwave region. So, microwave region of electromagnetic spectrum, also known as rotational spectroscopy. Here we can observe the rotation of the molecules. In a microwave region of electromagnetic spectrum, we can observe rotation of the molecules. For example, if you take molecules like HCl, HBr, etc., performs rotations about the central axis. The third portion from bottom to top, if you see, infrared region of electromagnetic spectrum. So, infrared region is also known as a vibrational spectroscopy. Here we can observe the vibration of the molecules. For example, if you take, we do not declare any permanent electric dipole, so we can calculate the vibrations of the molecule and we can understand the motion of the molecule in different ways. Where visible portion, here we can see all the things. Raman can able to see images, objects, everything in visible portion. Visible portion further divided into 7 colors from which you are to red. The wavelength of the red is greater than the wavelength of the violet. So therefore, the next reason of electromagnetic spectrum is UV. So here the source in Raman effect or Raman scattering is UV or visible radiation. So let us see diagram. For simple, better understanding. If this is a molecule, molecule means 2 or more atoms together form a resultant molecule. So generally the molecular spectra are a little bit complicated than the atomic spectra, because in atomic spectra involves only 1 electron, but whereas in molecule involves 2 or more atoms, so we have to consider nuclear interactions also, because 2 or more electrons are there and also 2 or more nucleus are there. So we have to consider interaction between electrons and interaction between nucleons also. So therefore the molecule is composed of 2 or more atoms. So when the UV or visible radiation, when a UV or visible radiation incident on a molecule, what happens? Generally, when UV or visible radiation incident on a molecule, the light UV visible radiation is scattered in all directions. This is happen after interacting with the molecule. So UV visible radiation after interaction with the molecule scattered out in all directions. So this scattered light, it is observed that scattered light not only consists the intensity which is same as that of incident light, but also higher and lower intensities. I mean higher frequency and lower frequency than that of incident light. Here 3 things may happen: either the frequency of the scattered light may equal to the frequency of the incident one, or the frequency of the scattered light may be greater than the frequency of the incident. Third one, either the frequency of the scattered light is less than the frequency of the UV or incident light. So number 1, if let the frequency of the incident radiation I. I stands for incident radiation. Nu generally represents the frequency. Nu I be the frequency of incident light. After interaction with this molecule, the light is scattered out in all directions. So therefore, the first incident, frequency number one, either the scattered light frequency is equal to the frequency of incident radiation. So this is known as Rayleigh scattering. For Rayleigh scattering, the incident of the scattered light frequency is same as the incident light frequency. This is known as a Rayleigh scattering. The second, it is observed that the frequency of the scattered light mu s is greater than the incident frequency. This is also observed in this event. The frequency of the incident light, the frequency of the scattered light is greater than the frequency of the incident. So the produce, when the Raman spectrum is produced, consists of anti-source lines. Anti-source lines. So if the intensity of if the frequency of the scattered light is less than the frequency of the incident light, then the Raman spectrum is produced Stokes lines. Actually, Stokes is in very species. These anti-Stokes and the Stokes lines are called, both these are called Raman lines. Stokes and anti-Stokes lines are called Raman lines. For Stokes lines, US is less than mu. I mean, if the incident frequency is less than the scattered frequency, the spectrum produces anti-Stokes lines. If the incident frequency is greater than the scattered frequency, produces Stokes lines. So this can be explained by a Raman shift. Raman shift delta mu. Raman shift delta mu is defined as the difference between incident frequency and scattered frequency. Now therefore, delta mu is equal to mu minus mu s. So either the delta mu is equal to 0, or delta mu is equal to positive, or the delta mu is equal to negative. So delta mu should be positive for the Rayleigh scattering, because the frequency of the scattered light is equal to incident light. This is for Rayleigh scattering. So the delta mu should be positive only when mu s is less than the mu I. If mu s is less than the mu I, then the Raman spectrum or the Raman shift should be positive. If mu s is greater than mu I, consisting higher frequency lines means lower intensity, then the Raman shift should be negative. So for delta mu is equal to 0 means more intensity line. The intensity of the Rayleigh lines is much greater than the intensity of the Stokes and anti-Stokes lines. Therefore, if delta is equal to positive means more high intensity. This is for the Stokes lines. For anti-Stokes lines, delta is equal to negative or lower intensity, less than intensity. So therefore, if you find the intensity relation between Rayleigh, anti-Stokes and Stokes lines, so the intensity of the Rayleigh is greater than the intensity of the Stokes, and it is greater than the intensity of the anti-Stokes. This is the relation. So these three things happen in the Raman effect. So based on the Raman shift, you can explain the reason for higher intensity. Why some scattered lines are higher in intensity, why some lines are lower in intensity. So therefore, this is the basic principle of Raman effect. Raman shift is equal to delta mu is equal to mu minus mu s. Now let us discuss the quantum theory of Raman. What is the reason for higher frequency lines and lower frequency? What is happening when the UV or visible radiation is sent by the molecule? Now let us discuss the quantum theory of Raman. You know classical rules like Newtonian mechanics and classical mechanics are not applicable to explain Raman. That is the failure of classical mechanics. So the classical, you know very well, classical mechanics fails to explain photoelectric effect, fails to explain Raman effect, fails to explain the transition between energy levels, and also fails to explain Raman effect also. So quantum mechanics succeeded to explain the Raman effect. Raman effect, known as a quantum theory of Raman effect. You know very well, the system here, the molecule and atom can be visualized as different energy levels. Let us see. So different energy levels. When your UV or visible radiation is incidentally area C, this is the energy level diagram. Okay, when UV or visible radiation is nothing but ultimately consists of photon. Photon have an energy hν. Photon energy hν. When a photon is incidentally on a molecule, by absorbing this photon, and already electron is available in this ground state, by absorbing this photon, the electron is raised to high energy state. If they return to same energy state, then the frequency of the scattered light is equal to incident light. Incident radiation. If the electron by absorbing energy, if they rise to high energy state, and if they return to same stage by using the same photon, then the frequency of the scattered light is equal to incident frequency produced and scattered. This is the first thing. Second thing, by absorbing the electron, so by absorbing the photon, if the electron rises to high energy state, if they return to the state which is above the ground state, then the scattered light frequency mu s is less than the mu I, then the Raman spectrum is produced Stokes lines. Already if the electron is in excited state, if they rise to high energy, if they return to the state which is below than the excited state, then mu s is less than mu s is greater than mu I, and Raman spectrum is simply consists of anti-Stokes lines. This is the simple quantum theory for Raman. So three things. There are three possible things. Either the scattered light frequency is equal to incident frequency if the electron rises to high energy and if they return to same energy state. Mu s is less than mu I if the electron rises to high energy if they return to the state which is above the previous one. I mean here for mathematical simplification let us define E1 and E2. So in E1 state as an energy hν, by absorbing this hν if the electron rises to high energy, if they return to E2, then mu s is equal to less than mu I. If already electron is excited state, by absorbing energy if they return to E1, then mu s is greater than mu I. And because the difference between these two states is equal to delta U. So therefore, ultimately according to quantum theory, delta E is equal to defined as delta nu by hc. So therefore, the Raman shift, which is directly represents the energy changes between the energy levels. So change in energy level. So here delta is equal to 0 or delta is equal to constant, delta is equal to negative. So delta is equal to 0 or delta v is equal to 0, delta is equal to positive or delta mu is equal to positive, delta is equal to negative or delta mu is equal to negative. So directly represents the Raman shift directly represents according to quantum theory change in energy. And also we know the transition between energy levels are restricted because here in Raman spectroscopy the possible selection rules are delta J is equal to 0, 1 plus or minus 2. These are the selection rules for Raman spectroscopy. You can see in rotational spectroscopy delta J is equal to plus or minus 1, plus 1 for absorption, minus 1 for emission, and remaining transitions are forbidden. Even in vibrational spectroscopy also, delta V is equal to plus or minus 1, plus 1 for absorption, minus 1 for emission. But in Raman spectroscopy, simultaneously we can observe rotations of the molecules and also vibrations of the molecule. So basically the Raman spectroscopy, Raman effect is treated as a vibrational spectroscopy for which the selection rules are delta J is equal to plus or minus 2. Delta J is equal to 0 is a triangle. This is for Harris character for which delta mu s is equal to mu I plus 2. So plus 2 for Stokes transition, Stokes lines transition, minus 2 for anti-Stokes line transition. Remaining are forbidden. Plus 2 for Stokes transitions, minus 2 for anti-Stokes transition. There are a number of applications based on this principle. So by using this Raman experiment, we can study the internal structure of the molecule or atom and vibrational energy level, vibrational energy, rotational energy, and also we can find the different mixtures involved in the system. So separation between the atom also. Okay. So the Raman spectroscopy provide lot of information than the bidirectional spectroscopy. So these are the selection rules. In next class, we will discuss experimental setup of Raman.